The PDF you find right now on my home site, that URL, is not updated. I prepared it a couple days ago, I've done some changes to the presentation since. I will upload the very latest after the talk. I, by the way, strongly invite you to interrupt me, give feedback, ask for clarification anytime during the presentation, because this is the first time I'm giving this specific presentation, and if there's anything that should be tweaked or whatever for tonight, you will help Google have a better impact on the Linux user group members. So, what's an object model? And more generally speaking, what's object-oriented programming, or OOP? This was supposed to come out of speakers, but I can't make the speakers in this room work, so you'll have to be very quiet and listen hard. Now, this is not the OOP I'm going to talk about. On the other hand, I'm going to talk about object-oriented programming, which is the concept of grouping, packaging, state and behavior in suitable chunks for three main purposes. And this should hold for just about any kind of class-oriented, object-oriented programming language, which is just about all of them, except maybe JavaScript or stuff. You want object-oriented programming to achieve delegation, which is a great-sounding task of letting somebody else do the job. And take the credit, of course, otherwise it's not fun. You want it for polymorphism, which is acting like somebody else. And you want it for instantiation, making one blueprint and several instances, objects built following that blueprint. We will be exploring these three issues. The issues are common to every programming language that tries to do object-oriented programming one way or another, as long as it does it through classes, which is the instantiation part, as opposed to prototypes, as in JavaScript or so. But specifically, Pythonic issues come up mostly with delegation and polymorphism, so we're going to devote by far most of our time to those, and just mention one very interesting and important point about the instantiation at the very end of the talk. What does it mean to use object-oriented programming for delegation? Well, there is intrinsic or implicit delegation each time you do an attribute lookup on an object. Let's talk specifically Python now. Each time you look up an attribute, which could be a method name, first of all, the instance delegates to the class. If the instance itself doesn't have an attribute by that name, no problem. The class is likely to have it. Every time you call a method, it's more likely to be defined in the class. So look at object-oriented programming this way, which may be slightly unusual. An instance, which is an object, delegates most of the attributes to the class, which is another object. The class itself, in turn, tries to get every opportunity to shirk its job by delegating it to descriptor objects, which we'll get into in a lot of details. And if that fails, to base classes, as long as it doesn't have to do the work itself, it's going to be happier. Moreover, besides the implicit delegation that happens on every attribute lookup, you generally use object-oriented programming to package up a lot of explicit, overt delegation through containment, also known as hold or wrap. We'll see the difference. Delegation to self, which is something that only works in programming, which is basically forcing yourself to do the job that you should do. Essentially, when we're talking about intrinsic and implicit delegation, we're mostly talking about inheritance and similarly specific rigid mechanisms. We're talking about containment, holding and wrapping. We're talking about much more flexible approaches. Another way to put it, which is classic in other languages, is to say that inheritance asserts an is-a, so it's basically something that is an existential relationship, while holding and wrapping is simply a commercial business relationship using a certain supplier of some service. So let's see exactly what we're talking about. Attribute lookup is the root of Python object-oriented programming. Each time you write x.y, you are participating in the great concern of Python object-oriented programming. By the way, whether you're going to call that y or not makes absolutely no difference. Most languages, for some reason, treat x.y and x.y open close paren completely different, like different namespaces. In Smalltalk, which is a great object-oriented programming language, you just can't, from the outside, look for x.y unless you're going to call it. Essentially, only the methods show through. In Python, there's absolutely no different. First, you do the lookup, the .y, and then you may do the call, open close paren, or you may not. So, from our point of view, this works exactly the same way. What happens whenever you do x.y? Well, Python, first of all, checks out all the descriptor stuff, which, as I repeat, we'll be covering in a lot of detail in a second. Assuming descriptor stuff doesn't pan out, well, first of all, Python is going to look into the dictionary of instance X. You may bypass dictionaries by defining slots, we'll see that, but that's a very special case. 99.9% of the time, you're looking into a dictionary. If that doesn't work, well, you try the dictionary of the type of X. This is what I meant by saying that the class delegates to the instance. Each class has its own dictionary, as well as each instance has its. Type X is the same, by the way, as x dot under class under. We're only talking about today's object model. We're not going to cover the legacy object model which Python carries around for compatibility with the way it was 5 years ago. If neither the lookup in X's own dictionary nor the lookup in the basis dictionary give any luck, then Python walks over the basis of X's type in a specific order, which we will not go into detail, which is called the method resolution order. For historical reason, it does not only apply to methods. It's an attribute resolution order, so it's badly misnamed. Okay. That's what historical reasons are for. Similarly, although much more simply, whenever you assign to x.y equals z, again, there is an attempt to let a descriptor do the work, and if no descriptor is available to be suckered into doing the work for you, then just set the thing into the dictionary of the instance. In this case, we don't delegate to the base, we don't go and delegate to the class, and much less to the basis of the class. Descriptors. Most of the time, we delegate lookups to descriptors. What does it mean? They're the key infrastructure of Python OP. I said the lookup of attributes is the key of object-oriented programming in Python, and descriptors are the key of attribute lookup. Essentially, attribute access in the generic sense, meaning getting most of the time, setting sometimes, deleting rarely. People rarely think about deleting attributes, mainly because most languages don't let you do that. Python does, but it just doesn't come to mind. But anyway, any of these kinds of access starts by looking at the type, and on the basis of the type, for the name you're trying to get, set, or delete. If a suitable descriptor is found in the type or some base of the type under that name, then everything else gets delegated to the specific method of that descriptor. What does it mean to be a descriptor? Well, it essentially means to have the special method under get under. If you have that, you're a descriptor. If you don't, you're not. That's very simple. By the way, when I say have a method, particularly for special method, it always means the base has it. We will get into that in a bit more detail later. But in the Python object model, the intrinsic lookup of special names doesn't look at the dictionary of the instance, doesn't even try to. It works strictly on the type. So that will come up over and over again, but I just wanted to make it clear. If a descriptor also has a method called set under, it is known as a data descriptor. For historical reasons, a much better name is the one we use today, override descriptor. But you will find data descriptor a lot in the literature, including Python in a nutshell. What does it mean to be an override descriptor? It means that the class, or rather the descriptor held by the class, overrides the instance. So you don't get into, you don't even look at the dictionary of the specific instance if you found an override descriptor. If you find a descriptor that is not override, you still have to check the instance of the dictionary as well. And there is no special name for that. It's just a non-data or non-override descriptor. So what does it mean when you have an instance of class C, we call it X, and you access, as in get, x.foo? You read it. Well, if the class has an attribute named foo, note that this already implies all the lookup over the basis. Anytime you say has after, the semantics of that, or get after or whatever, the semantic of that is to look into this thing and all of its base classes. So we don't have to spell it out.
So is a class instance shared among, I mean, is a class variable or class attribute shared among all instances of that class? Yes? So
Yes.
It's basically a static variable or a static member?
Or static method. Or not static, really, but method.
Okay.
It's a descriptor is in the class. All the instances of the class can use it unless they're instances of some subclass which further overrides it.
Okay.
So we get that attribute from class C. We get the class of that attribute, the type of that attribute specifically because we only want to look for special method in the class. Now, if that class has that under, get, under, then we have a descriptor. Before we can use that descriptor, we need to check that either it's an override descriptor or it doesn't need to override anything because the name is not in the dictionary of the instance. If so, then we can finally delegate to under, get. This is very pedantically to write d.classnet.under, get open instance, blah, blah. I would normally write that as instance.under, get argument. But the point I'm being pedantic about here is that it doesn't matter if the instance itself has something called per instance in its dictionary called under, get. It's not even looked at. We only go to the class. So if it's not a descriptor, or it's not an override descriptor in something in the instance, or it is, no, those are the two negatives, then we go to the dictionary of the instance, or we get it from the classes, or we go all the things I mentioned in the previous slide. But this nested set of tests is what determines whether we can override, we can delegate to a descriptor for a get operation, a read operation. Write operations are simpler. Essentially, again, if what we're trying to write is in the class and it's a set, it's got a set method, then that set method is what is supposed to be doing the setting. Otherwise, the setting is simply in the dictionary of the instance. No looking up the classes or whatever, as I mentioned on the previous slide. Okay, so what is this all for? Well, one crucial issue is that in Python, every function is a descriptor, meaning the type of functions defines a special method under, get under. Therefore, you can, well, call it. And what happens? Well, the semantics of under, get are up to the specific type. In this case, what happens is that the argument you passed gets bound into the resulting callable. So the resulting callable has the first argument predefined. Calling add23 of 100 is like calling adder of 23 100. If you look in more detail at that add23 in your Python interactive prompt, you will see it claims to be a bound method type int. Now, since you know perfectly well that type int doesn't have anything called adder, you may be inclined to be a bit suspicious about that. How can it be a bound method? Type int doesn't know anything about it. True. It, however, knows about type int, and the reason it knows about type int is that it was bundled with an integer argument. So essentially, the type doesn't need to know anything, because all of the work is done in the under-get method of the descriptor. Now, as it happened, we cannot add a descriptor to type int. Built-in types are not available for our modification in this way. But we don't need to, because we can do exactly the same job from the outside. That is, from the function itself. This is the mechanism whereby, yes.
So is this basically a way of currying or part
Yes.
of application?
This is a limited, because it only works for one argument, and it must be the first argument, and so it doesn't have the full flexibility you would like of partial application, or as I still prefer to call it, currying, although some people think that currying is something else. I see you don't serve curry here, so the problem doesn't apply. So instead of a plate of curry, I decided to illustrate this.
I have a cunning plan.
A different kind of adder, but a black one. But it sounds much better when I do have working audio, I swear. Anyway, basically, this is I'm showing it in an anomalous case, but this is what is happening every time you call a method in an instance. It gets bound this way through the under-get method of the function, of the type of the function, and then upon call, the first argument is returned. An example of descriptor that didn't used to be in Python 2.2, but we are apparently managing finally to release Python 2.3 everywhere. I think we still, yes, I have an email in my mailbox that claims we're doing that today. MSB Simulator, 350,000 machines, Python 2.3, 2.3.5. So anyway, so we finally can use property and not feel guilty about it. This is a custom descriptor type. There's a few chairs if somebody wants. Maybe the position isn't optimal, but we can certainly move them somewhere else. There you go.
Thank you very much.
A property is a special purpose type of descriptor. You build it by passing it up to 4 arguments. One of them, and I really think you should always pass it, is a string, just a doc string for that attribute. That's very useful, and it doesn't do any damage, so pass it. The other ones are optional. Generally, you will always, almost always pass. Oh, this is, whoops. You will always pass the get, because that is the function that's going to get called when the attribute is read. Maybe the set is going to get called when the attribute is set, and this is going to get called when the attribute is deleted. If you don't pass something, it becomes an error. You will get an exception if anybody ever tried to say delete a property for which no deletion method has been supplied. The signatures are very simple. The get has to return a value, the set has to accept a value, and the del doesn't have to do either. And this is a totally trivial example where the set and del let you set the attribute to anything, delete the attribute, and they don't do anything and simply hide the thing from you. This is not recommended technique, just to show how it works, and then wherever you get its value, you get a constant. And this is the built-in bar. Anyway. A doc string you should always pass. As you don't have to use the next, of course, anytime you call Python with. There is a tricky issue which may. Yes.
How do you use that?
By the normal syntax. You instantiate foo into f and then say f.bar. Print f.bar will call the get and will print 23. Okay. You can say f.bar equal 947. That 947 will be totally ignored and go into the either, and it will still be 23. You can even ask to del f.bar, and it will just continue, say as if deleted, okay, but it's still there. So.
What about the doc parse, the text? The
doc is something that helps if you want the help on an attribute. You can get help or just print a doc, but help is a normal interactive way. And depending on what interactive development environment you're using, documentation strings can appear like test tip or that kind of thing. But hopefully more informative than that. There's one tricky issue with property and inheritance. The way properties are constructed today will probably go away in Python 2.5. There's a strong proposal for that, but it will be a long time before we move to Python 2.5, so it's important to understand the issue. You say you have a base class in which you build a property. This is a property which is only a getter. Now, what is happening? You're passing the getFoo object which you just defined. That getFoo object, no other. So what will happen when the property triggers? It will call that getFoo object, not another, under any circumstances. It will call the one you passed it. So if you somewhere else, for example, in a derived class, define another object with the same name, the property will not even know about it. So you instantiate the derived, you print d.foo. This thing will never get in play. Nobody will ever hear about it. This thing will get in play. So you get 23. So the normal way this gets expressed is property doesn't work with inheritance. It does, except you have to do some work to make it work. Inheritance is a complicated thing. This is Mendelian inheritance. I couldn't find a good diagram of multiple inheritances. The simplest fix until today, until you get Python 2.5 with it fixed, is to add an extra indirection, which validates one of the oldest rules in computer science. There is no ill that cannot be solved by an extra level of indirection. It works, even in Python. Essentially, instead of passing to the property constructor, I'm giving the bad example and stopping writing doc strings. I'm just want to be more concise. Instead of passing the thing you want to override, pass something else which does the lookup. So the point is that overriding by inheritance works at the moment you do the lookup of the attribute. So you want to do it as late as possible, late binding ways. Normally in Python you get late binding whether you want to or not, roughly. But in this case you have to actually ask for the late binding because property binds early, binds when it's constructed. So have it bind fooGet, and fooGet does a lookup, and now they derived work. You can also see this as an example if they I'm going to enter it in the Guinness Book of Record as the simplest possible example, or useful example, of template method design pattern. We'll talk about template method and other designs pattern later, but the template method design pattern is where an organizing method called hooks method within the same instance. It's the self-delegation thing. Well now, here, this fooGet is an organizing method. It doesn't do much organizing, but it does do one call to a method which is meant to be overridden, a hook method, which here we call get.
So what's the solution? Just to pass the name of the function you want?
That is what Python 2.5 is probably going to do, is to accept instead of the function, the name, and then they do the lookup for you inside. But it won't be around for a year, so don't worry about it. Yeah. So, besides the descriptors that Python gives you, which include as well as functions and properties, such things as static method, class method, you can write your own descriptors. Most of the examples here, the non-trivial examples in this talk, are taken from the second edition of the Python cookbook published by O'Reilly. I don't know if you have some copies around, but they're pretty easy to get. You can also get all the code only, just download it from the O'Reilly site. Having written the text, I think the text has some value, but Don't get that gets something. For example, what could we use a custom descriptor for? Well, we could use an alias attribute, a form of delegation. Each time somebody asks for attribute foo, give him attribute bar instead. Why would you want to do that? Well, you might want to have two names for the same attribute for several reasons, and one of the best one is for the unconditional alias attribute use case. You released a previous version of your class where you named something very bad name. You named an attribute very bad name. Then and that was released. Then on mature reflection, you release that name isn't really good. So you want to rename it to very good name, but a lot of client code uses very bad name. So what you do? Well, aliasing it, and possibly with placing a warning each time the very bad name is used, still let old code work, because the very bad name gets redirected to the very good name and gets some warning, so eventually the code will get fixed. That's one example. So how do you do that? Well, at each time you have to record the name, which you will be indirecting, and upon get you have to check, because, sorry, this is, I said obj here and inst here, this needs to be obj. Need to fix this. I could claim a typo, but enst is rather distant. So I'll claim a thinko, sorry. Basically, the get is going to be called without an instance, without a specific object, when it happens on the class. And when that happens, most descriptors that don't need to do anything weird on the class will just return themselves. So otherwise, it does a attribute lookup on the object of the name. It knows it alias it to. Now this default alias is overridable. It's not overriding, it's overridable. It only has a get. So if somebody sets this attribute, the setting takes precedence, and from then on, that particular instance doesn't have an alias anymore. If we inherit and add a set, and also a del, then the setting on the instance will also be redirected through this, as will deletion, just to be complete, and that will be all. There will never be any change to the descriptor. All the changes, assignment to the descriptor, will go to the real attribute that recovers. By the way, the real attribute could also be any kind of property or whatever, because we do perfectly normal lookups, get after, set after, del after. So we're using all the normal Python mechanisms. Another example of custom descriptor is, say there is an object which potentially has a huge number of attributes, which may take substantial time to compute. This is actually was my use case, and the reason I really thought about that. My first use case for Python was a contract bridge programming system. So I had an object which was a hand of bridge. And a hand of bridge can be evaluated according to 1,000,000 algorithms. You can ask for a distribution shape, points, losers, controls. There's so many things. If I computed all of them, I'd never be done. However, I wanted the object to hide all of this, so all the rest of the system could just ask for any attribute of interest, and the object would compute and cache it internally just in time. So I built a very ad hoc system for what can be now done in one slide. Essentially, the JIT attribute descriptor, you basically pass it a method. Note that by passing a method rather than a method name, we have built in the same inheritances as properties, so you may want to add an indirection to fix them. If there is no, I default the name from the method, you could do the reverse. At get time, again, if obj is done, I got it right this time, return self, meaning for lookups on the class, just pass through. Otherwise, do the computation, and this is a tricky part, set the result of the computation on the specific object under this name before returning it. This is essentially not only an overridable descriptor. It's a self-overriding descriptor. The first time you ask for it, it overrides itself at that instance by this set item. So any future request will not repeat the computation, will just get the cached instant. This, of course, assumes sort of immutable things, because this value is going to be computed only once. The first time, if any. The main point is not so much the caching, which can be done much simpler ways. It is the fact of not even doing the computation for those 99% of potential attributes that are never actually requested. This also happens a lot in signal processing. If you have an object that represents a certain signal, the amount of things you can compute on that signal, the amount of transforms and is boundless. There's easily millions and millions. You don't want to compute all of them in advance, but computing them just in time works just fine. Again, treating a signal as an immutable object is particularly useful. Back to more normal delegation, I have claimed there is a distinction between holding and wrapping. They're both kinds of containment in the contain and delegate usage mode. Holding just means that a certain object O has a certain sub-object S as an attribute, and that's all. The attribute could be a property of something fancy, but that will be totally transparent from the outside anyway. So essentially, you just want to call some method on the sub-object, you do. You do. You call within the object self S method, from the outside O S method. It's simple, it's direct, it's immediate, it's wrong. Why is it wrong? Well, sometimes it isn't, and it's a matter of degree. But it's coupling things in the wrong axis. The use of self-S method is fine. The point is, I cringe every time I see an O.S. method. It's coupling on the wrong axis. You have committed forevermore to the fact that object O will have a sub-object S, which will have an attributor method with that name. And if this happens with 2 dots in an expression, you can survive it. But once you start along this sloping plane, there's no stopping. And soon, that again, this isn't specifically a Python issue. You'll find it in Java code, even C++ code. If there's more than one dot or arrow in the case of C++, doesn't make things any better. If there's 2, there's 3, there's 4, there's 5, your code is unmaintainable. You are implying, exposing all the structure. You will never be able to change the implementation of your code without breaking all of the client code. The way this is most often expressed in undergraduate courses nowadays is as the law of the meter, which is sort of a fancy way of putting it. The simple expression is, if there's more than one dot, that code smells. And you know, code smell is a technical term, so I'm not saying it actually stinks. You should investigate it. How do you avoid excessive dots? The simplest way for this very simple case is, instead of just holding another object, wrap it. That is, hold maybe be a private name to remind yourself and your client that this shouldn't be accessed, and delegate to it. So you use O dot method, you call the method on the main object O, and it internally does self-S method. Or implicitly, that's what we have Generator for. You don't even have to code out all the boilerplate whereby all the delegated methods get passed to the sub-objects. Yeah?
So is there any way in Python to avoid the overhead of a function call for doing this wrapping?
If you're...
Because I know that the function call overhead in Python is a lot.
If we're talking about non-special method, and if your profiling determines that every nanosecond counts, we're not talking about huge gains. But you can extract the function call. You can extract self-S method into and then say method self.method equals self.s.method. You're not saving a function call, you're saving a lookup, which isn't quite as fast.
Oh, really?
How you have to call it a function in the end.
Well, but if you have the explicit one, then you have a whole function to do that lookup. So if you can only
So you could do the lookup when self-s is set. You could look up all the things you want to delegate to and save them somewhere so they won't have to be looked up again. And there's some people who swear by that optimization. I've measured it many times. It's a microsecond thing. It's not huge. Some lookups can take a lot. I mean, I have described, of course, sort of conceptually the lookup process. And if a lookup needs to be very sophisticated, it can do several steps. But it will still take a couple of microseconds unless it gets into, okay, so, and now I send a request to the database and wait for results as part of your lookup, then maybe you should redesign your approach. You can save something by doing lookup in advance. If you don't need the flexibility of late binding, you can bind earlier. I mentioned earlier a case in which things got bound a bit too early, meaning it's faster, but it may want to delay the binding. The reverse happens more often, I guess. But you will not have huge savings. One example of where wrapping is particularly appropriate is when you want to restrict an object. This is not exactly the same thing, but it's akin to the design pattern known as facade. So you have this object which does a million things. You need an object that does 3 things, which happen to be among the millions. Great. But you don't want to expose the other 999,997 because they're attractive nuisances. You don't want your client code to call those other methods. What you're supplying conceptually is a thing that does 3 things. So how do you do that? This is normally found as requests for, okay, I'd like to inherit from X, except I'd like to be able to remove its methods or attributes ABC. How can I do that? The answer is you can't. Inheritance does not let you restrict the interface. By definition, inheritance asserts that something is a something else. So no amputations allowed. What you can do with the same effect is wrapping to restrict. You can, for example, this is a generic restricting wrapper, take a block, which is a set of names you want to block, record the object you're wrapping and the block, and every time somebody tries to get an attribute from you, if the attribute name is blocked, you raise an attribute error. So nobody will get through. Otherwise, you delegate to the wrappee. This doesn't work for a special method. Special methods require special care, we'll see it later. But mostly, that doesn't work because special method needs to be looked up on the class. So if you want to have a class with a subset of special methods of another class, you need to build it on purpose. This only works for normal, non-special applications.
You're wrapping an object here.
Yes.
Could you wrap a class? And
Yes,
class?
I'll show that later with a bit more. The normal way to wrap a class would be to use a meta class. I'm not getting into meta classes in this talk, custom meta classes. So I'll show a more ad hoc way later. Okay, I have sort of mentioned in passing one of the most important design patterns, not just in Python, in every programming language, which is known as the template method design pattern. My opinion is that it's a great pattern with a lousy name because the word template is way too overloaded. Besides they use to describe generic programming in C++, it describes a crucial technique to generate, for example, web pages or HTML documents by starting with a template one and then filling the blanks, which has absolutely nothing to do with the template method design pattern. So I prefer the much more descriptive name of self-delegation. The only disadvantage thereof is that I'm the only one using it. So if you say self-delegation, nobody will understand. In the classic version of template method, there is an abstract base, not something you're meant to instantiate, which offers an organizing method. Clients call the organizing method. on instances which, however, must be of concrete subclasses. The concrete subclasses must implement certain hook methods, and the role of the organizing method is to call the hook method in the proper sequence and so on. There's a variant which you will have met if you're into like C loops and other languages heavy on mixing, where basically they mix in base offers the organizing method in the concrete classes. We'll see both examples in a Python setting. The best example of template method design pattern I've ever seen is in, and no limitation to languages, is in the Q module of the Python standard library. The Q class is the Q module in the Python library. For example, if you look at Q.put, which is a thread-safe, first in, first out Q, the put adds a method, it acquires a certain, I think not full is a condition variable, waits for, it keeps looking and calling wait on the condition by calling a certain underfull method. When it's here, it has acquired the lock, there is not a full condition, it can safely call self underput. And then it notifies another condition variable called not empty. In the typical try finally pattern, it then guarantees it has released the not full. I'm not getting into Python threading now. I assume you know what acquire, release, and wait mean, and so on. What I'm trying to point out is that the real job, after all of this infrastructure related only to threading, is done by calling self-underput, which does nothing but a self-queue append. So one could wonder, so why, instead of striving to avoid a function call, why is this guy putting in an extra function call? Is he like an indirection freak? The point is, you can override this one. Note the differences between the Q concept of a template method design pattern and the classes. Q is not abstract. 99% of the time you'll just use it. It's perfectly good. It has an implementation of all the hook methods. And for example, the underput hook method is very simply implemented as self-queue append. But you can subclass. And the reason you subclass is to customize the queuing discipline. You don't have to worry about being thread safe. All of the locking and the timing is guaranteed for you by the organizing methods, which are the ones that client code will call, get, put. You can override underget, underput, underfull to use whatever queuing discipline you want. The default is the simplest and most useful, which is why 99+% you're using it is first in, first out. You can override under init, under queue size, under empty, under full, under put, under get. You can also override data. This is not something you probably think of in most other object-oriented languages. You can only override method. In Python, you can override data as well. It does sometimes. Not in this case, I just want to give an example of data override. For example, say that I want a queue that needs to be last in, first out. I can't think of a use case in which I would want a queue for communication between threads to be last in, first out. But the point is, I can do two examples in one slide as well. Because I can do it with using the dequeue, double-ended queue, which queue itself normally uses. I simply have to change, override underput to do an append left instead of the append. Append means append right, the terminologies. Append means at the end, append left means at the beginning, if you wish, in a double-ended queue. And this, of course, by appending at the same side on which data are taken, I have a last in, first out instead of first in, first out. That's as simple as it is. Or I could say, hey, I only need a a stack, a last in first out stack. It's a waste to use a double-ended queue and then use only one end of it. Well then, I can override under init and make self queue a list instead of a double-ended queue. And then the put using the append is fine, you just need to change the get to use the pop. Append and pop are the same as push and pop with neuromorphic stacks. So you can make advantage of the template method design pattern by changing queuing disciplines without having to worry about the really difficult part, which are the threading coordination. Another example of template method design pattern using the Mixin. It's user.dict Mixin, again from the Python standard library. First of all, it is abstract in that you cannot instantiate it. It's not so much intended to be subclassed as to be multiply inherited from, but you could subclass it if you wish. There's no blockage against that. The fact that it's abstract means it doesn't implement its own hook methods. That's the crucial distinction between an abstract and a concrete organizing class. So therefore, the subclass must supply all the hook methods. What are the hook methods for dict mixin? The very minimum, at the very least, you have to supply two. Keys, you must be able to return a list of what is a valid key in your mapping, and under get item. That is, you must supply a mechanism whereby, given a key, you can get the corresponding value. Nobody else is going to be able to embed those for you. Similarly, if you're doing a read-write mapping, you should also supply ways to actually set an item or delete an item. Normally, you want your mapping to be initialized. You have some work to do at initialization, so you supply under init. Normally, you want it to be copyable, so you supply copy. And this is all you really need to do. Everything else in the extremely rich map interface, which is the mapping class, the class does for you, the Mixin does for you. However, it does it for you in a rather generic way, so if you need performance, you may override more and more methods. You may also, of course, choose to implement all the methods yourself and not use dict mixin, but dict mixin is nevertheless pretty nice. For example, say you don't want to bother with implementing a has key. Well, you can avoid implementing it and inherit it from dict mixin. Because it will try to get self of key, which implicitly called get item, and in case this is a key error, it will return false, meaning no, it doesn't have the key. Otherwise, it will return true. Note, contains, the special method is implemented the same way. This would not work optimally. This would be too early binding if you did that. If you, instead of def contains return self as key, you had contains equals has key, the binding of contains would happen right then, and overriding has key would not change contains. In this way, if you override has key, contains uses your overridden version. This is one example. You might want to override has key for speed. If you have a faster way to check if the key is one of the keys of your mapping, you don't have to rely on raising an exception and catching it, which isn't particularly slow, but isn't blindingly fast either. Why would you want to use dict mixin? Well, for example, say you want to chain mapping. You have multiple mappings in a given order, and you want to build a virtual read-only mapping which is able to look up in the first, and if not there in the second, and if not there in the third, and so on. You chain a given sequence of dictionaries. How do you do that? I mean, there's so many things to implement in a dictionary. Yes, if you want to make a real complete mapping interface, but you can let user dict mixin do most of the thing for you. Just to record the set of mappings. When you want to do a get item loop along all the mappings, trying to return the result for each and ignoring errors. If you fall through, the key is nowhere, raise a key error. And for the set of keys, we built it with a set. In the end, we need to make it into a list. That's a formal requirement. It is, of course, going to be in a mess of an order, but as you well know, keys doesn't have to guarantee order at all. Dictionaries are generally hashed, so order is irrelevant. Okay, we are running very late, so unless somebody is particularly interested in state and strategy, I'm going to skip this part and move right on to polymorphism. Polymorphism means working like something else. In some statically typed method, you need to use object-oriented methods to be allowed to do polymorphism. You need to do inheritance to be able, or something that looks like inheritance, like in C++, you use exactly the same syntax to say you're implementing an interface as to say you're inheriting from a class, while in Java you use two different keywords, but the semantics are identical anyway. Now, this isn't very relevant in Python, although people keep wanting it and making interface systems and so on. You normally just use duck typing for that. However, we are still interested in more advanced concepts of polymorphism, such as all the adaption and masquerading design patterns. I can really get very deep into those. I have a separate PDF on those on my site. The overloading of special methods to be polymorphic to a sequence, polymorphic to a number, advanced control of attribute access, and custom descriptors and metaclasses. We will not cover metaclasses in this talk. Good thing too, since we've got about 6 minutes left. So we don't really care about the need, because this is the secret to Python's productivity. We use duck typing. It takes a while to teach the duck to type, but after that, it's very fast.
Here is the viaduct leading over to the mainland. Why not? I'm all right. How are you?
I'm sure a chicken typing would work. But why not? Anyway, sorry, that is. For example, let's give into an example of advanced control of attributes of attribute access. We might want to make a class such that nobody can add new attributes to its instance. Why would that be? I have no clue. I have never seen a convincing use case. And yet, it is one of the most frequently asked questions in my lifetime as a Python expert. But if somebody could add an attribute foo, yes, and so what? I've never been able to get a convincing answer as to why that is. However, although I cannot know why you would want to use it, people do. So I've come up with this. Restricting attributes, right? Essentially, whenever, after all the work leading to descriptors and so on, a special method that gets called if it's present is setup. You need to take responsibility for all the setting of attributes if you implement setup, because it gets called every time. It gets called with a name and a variable. And in this simple class, we say, if self doesn't already have the attribute n, then it's an error to try to set it there. Otherwise, we delegate to the superclass. I'm not getting into the super special assuming. Now, of course, this might look a bit, wait a second. If we scream blue murder every time we try to put in an attribute that wasn't already there, how does it get there in the first place? Is that catch-22? No. This is how it gets in. Remember, I mentioned that has-attr does all the delegation game. So it doesn't, has-attr doesn't mean it's in this particular instance, it's in this instance, or its type, or any of the bases of the type. So basically, any instance of foo has-attr bar and vals. This is not a trick. This is exactly the root of Python OP semantics. So this actually works. And it avoids all of the issue with the technique that people try to use sometimes for the same purpose, which is under blocks. which gets killed by inheritance, and so on. It's got 8 bazillion issues. Forget about that. If you want a class to which no new attributes can ever be added, this is it.
Can you go through it again? You say it's a sense of Python OP, and I didn't really catch what's happening here. It's not calling this function when you do the bar bar is equal 1, 2.
Exactly. Because this is setting them on the class. Remember what I said about special methods are not looked on the specific object. They're looked on the type of the object. So, setting something in the class foo doesn't depend on the citator of class foo, but on the citator of the meta class, which are not calculated. But anyway, this by always systematically looking up special methods only in the type, you get all of these very clear, very sharp semantics. Yes?
Which is, I mean, the assignment statement in foo isn't doing a set adder on anything.
Not directly, no. No. The attributes are set by the meta class, not by Python itself. That's true. I didn't want to speak about meta classes today. It's hard to avoid, but you're right. So, before you use it, think of ugly. But the point is, use slots only to save memory in classes that don't need inheritance, don't need behavior, don't need anything, have huge lots of tiny instances.
Sorry, I don't really know what slots is.
Under slots is a class attribute which you may define. It's a tuple of names. If you do define it, there is no dictionary in the instance of that class, unless inheritance. If you don't have any inheritance, if you don't do anything except the one use case is class point object. Under slots equal x and y, open paren, quote-x, comma. That means each instance has an x and a y, and that's it. Nothing else. No flexibility, no behavior. You don't forget inheriting, forget having inherited from. You just want to have 1,000,000 points. You can save 12 bytes per point. It's a substantial saving. If you don't plan to have 1,000,000 instances, forget it. But if you are doing points, then 1,000,000 instances is reasonably realistic. Whenever I talk about advanced techniques, I want to always insert a slide because it's one of the crucial principles of programming. Ain't gonna need it. So don't prepare these things, prepare them in your mind, but don't put them in your code unless you have a specific use case where you really, really know they need it. I can also, of course, take out fire. Okay. This is sort of the reverse. It's, I like the flip side of rats. It's the ability of using a class instance as a module. Why would you do that? Well, for example, to be able to have constants, which means something different from, okay, we saw rats, which means no new attributes can be added, but the existing ones can be changed. For constant, it's rather the existing attributes cannot be changed, so you can add new ones. And how you do that is again a set after, but in this case, the condition for being an error is sort of the reverse. It's an error to set an attribute whose name is already in the instance dictionary. But how do you do that on a module? Modules don't have set after. Well, the answer is you make an instance of this class and set it as if it were a module instead of the module in which you define it. And this is modules. Second, this is a typo. It says modules. Okay. One more thing, which is sort of doesn't really fit very well. There are two ways in which you can build callables dynamically by calling another callable, which is a factory for them. One is very simple. It's the first thing that comes to mind if you've ever used this for whatever, and that is a lexical closure. A function nested inside another function, which can carry around and use the lexical environment. Essentially, an inner function with an outer function can use SRs, but also whatever was here. Or an object with an init and a call. Now the point is that the closure factory is simpler and faster. Although it will not be what comes to your mind if you're used to C++ or Java, where you cannot generate functions at will. In Python you can, and the key issue is def is an executable statement. There is no such thing as a declaration in Python. Def creates a new function object, dynamic runtime always. So when would you want to use a callable instance ever? This is one example. With closures, you have to forget subclassing. There is no such thing. You can't. So you cannot have a base closure and subclosures. For all of that, you need classes. This is, for example, say you want a subclass for to use a template method design pattern. You can do that, but only with a class. So if the class is more powerful and flexible, shouldn't we always use it? No, that's not Python philosophy. Use only as much power as you need. Don't use a thermonuclear bomb to chase a fly. That would be overkill. Use a swatter. Yeah. Thermonuclear bombs are more powerful. Use them advisedly. Okay, now I did mention a couple of times that the specials come from the class and not from the instance. So how do we build a restricting wrapper that fully takes advantage, fully covers specials? We build a class on the fly. The same issue. Like def, class is not a declaration. There's no such thing as a declaration. When you run a class statement, you create a new class. So we subclass the restricting wrapper we saw a few slides ago, and then we loop on the specials that we are okay with. I'll show, that is a pretty easy filter I'll show in the next slide. And then we define a function, a closure actually, and that again, see, for something def, this def will be executed each time we step into the for. It's an executable statement. And we set it as the attribute in the class object, and then we instantiate the class, and that's it. And this is the way to tell, to skip the names that are in special, skip the names that are in blocks, skip the names that are already known in restricting wrapper, and avoid get attribute because it will trip everything up. That's okay, you never need to block it up. Finally, we are getting very close to the end as well. Object-oriented programming is very handy for instantiation. Make a blueprint once and as many instances of that blueprint as you need. Same behavior, distinct state. The behavior being per class and the state being per instance. At rare times, we don't really want that. We want some of the other cool things, features, as I think I spelled it right, that object-oriented programming gives us. We want get-attr, we want inheritance, but we don't want instantiation. We only want one thing. So, since we don't want to have many instances with distinct state, we can forbid the thing in two different ways. We can forbid the many instances, and this is a traditional Singleton pattern, or much more effectively, we can remove the distinct state of chaining the monostate pattern. Singleton.
There can be only one.
I prefer Highlander. There can be only one, that's the new special method of a class gets invoked whenever the class is instantiated and may return a new instance, or it may punt and return an existing instance. And this is what it's doing. If there isn't already an int of the class, then it makes it by delegating the new to the super class. And finally, it returns that. This is a traditional Singleton design pattern, and it was new in Python. It very smoothly implemented. However, how do you deal with subclassing? It's one of the things you may want for, I mean, you don't want instantiation, but you still want a class because, for example, inheritance is cool. Yes, well, say that foo and bar both foo claims to be a singleton and bar claims to be a foo. Well, what do you do in this case? Because if you make to separate, if f and b are two separate objects, sorry, if f and b are two separate objects, then foo has two instances. Because b, being an instance of a subclass, is also an instance of foo. So you're breaking the crucial thing that there must be only one instance of foo. If they are the same object, what are they an instance of? How can they cannot be an instance of just foo, because then b would not be a bar. They cannot be an instance of bar because foo might have multiple subclasses and can be an instance of all the subclasses. Subclasses can be added. There is no way out of this logical maze. Singleton is a flawed pattern. Never use it. It's evil. It cannot do what it claims to do, if you care about inheritance at all. I'm amazed that the gang of four never noticed that. If you read weaving pattern, please see this weaving pattern, it keeps going around it. There's a solution. Sure.
We are the Borg. You will be assimilated.
This is not.
Resistance is futile.
This is not Google's Borg. This is the other Borg. I named this pattern this way before I joined Google. So. Essentially, let there be as many instances as you want. Just all share state. What does it mean to share state? Well, it means to share a dictionary. Specifically, let the class have a shared state dictionary. Whenever a new object is asked for, well, this makes a new object by Supra, and then the dictionary of the new object is replaced with the shared state. So essentially, all instances share the same instance dictionary, the shared state of the class. And subclassing is no problem, because you decide when the sharing gets broken thanks to data override in Python. This is what makes Python so incredibly good for this. Because, for example, bar and foo use the same shared state from Borg, but bars gets its own shared state, so it doesn't share with bar or foo. There is a superb article about Singleton and Monostate by Robert Martin, one of the best-known writer on object-oriented programming. He carefully examines all the pluses and minuses of Singleton and Monostate, and completely forgets to check whether that applies to Python, and shows that they're both a disaster in Java or C++, and basically there is no way out, no good solution in either Java or C++, which are his two favorite languages. But I invite you to Google for it and check if it's not true that this little thingy here satisfies all the constraints. It's a perfect implementation of the non-instantiable thing. Unfortunately, each time I try to explain that to Guido van Rossum, the inventor of Python, he runs away screaming, but one of these days I'll block it. He claims this is evil. Ah, well. Resistance is futile. Anyway, that's it. Sorry for taking you over.